Start that again. For those that had the without sound mumbling to myself, my name is Bob Grenier and I'm a volunteer with the Martin Fleischmann Memorial Project. So thank you for joining me this Friday night, the 22nd of April 2022. Thank you, Artifact, for telling me there was no sound in my initial mumblings there. Yeah, I had a different setup for the SEM EDS recording during the last 2 weeks, and so I had to just switch that over. Excellent. Thanks, Rhett, for confirming that. So really what I was just saying was that I have to thank all those people that have enabled this process of learning for me personally to happen. Those people like Tesla, who showed what was possible, Henry Murray, people like Yul Brown, like Joseph Papp, but particularly I have to say thank you to John Hutchison for just being him and the curious cat that he is, and exploring the work of Tesla and building on that with RF frequencies from old equipment, and showing really to everyone what was possible, not necessarily how it was possible, but what was possible. And then thanks to him, that inspired one Ken Shoulders to get involved and do an exploration of what was going on in John's work, and that led to the 1980s book called EV, A Tale of Discovery. And thank you to Ken Shoulders posthumously for releasing that in such a way that he could release his patents and other information such that the world could have an insight into his mind and what he believed was going on in the work of John Hutchison. And of course, he built on the work of Winston Bostick and the people of that Manhattan Project type era. And we're going to see a couple of those names like John Wheeler and his student Feynman, who also gave understanding to this process. But really, for me, one of the key players here is Takaaki Matsumoto, Dr. Takaaki Matsumoto. And I have great news to report. We now have email contact with him. And so I think it helped that we got this out of the door. It was a mammoth effort, but it's done. And we're going to refer to a couple of sections in this book today, and that will help us to understand what's going on. But I think with the SEM session, if you recall, the first ball that I saw, which I called the magnetic core of ball lightning, and I'll explain why I had the intuition that that was that again, for those that don't know. But anyway, I saw this thing and I thought, well, I'm going to have to, when I can next get an opportunity on the SEM, see if what it is, what I think it is, and whether there are any more on the Vega Valley. Now, the Vega Valley, what is that? It's various experiments in glowing action, and an experiment conducted by Henk Urian in Holland. And it was actually something that he did before contacting me, and he sent me a picture of it, and I said, I want to look at that. I want to look at that in great detail because I noticed the magnetic fluid structure of it, and that tied into my nascent understanding of this fluidized electrons that Ken Shoulders had been talking about, and I wanted to see whether that was actual reality and what was going on under the hood. So when we found in this valley over here, these balls, the one that I have on the wall over there, and we revisited that this week, and we know exactly where it lives, and the one that's next to it, which is largely identical in size but different obviously in its unique nature, its unique fingerprint that they have. It was just an honor for Henk, for me to have the opportunity to analyze that. So I must say thank you to Henk, and for all that work, all the work that inspired, particularly with Dave Boutillier, because the work that we saw coming from Henk's experiment inspired David to take it to the max, and we saw all of these structures coming off in high fidelity, which looked like all of the strange radiation tracks that had been observed over a long period of time with various researchers internationally. And so I believe that whilst this will not be finessed, it would be rude for me not to share with you what I saw on the SEMs. Now, obviously you saw the live session, but in part of that live session, I zoomed into something I thought was interesting and then zoomed out. And it was only when I was considering that on the train home that I thought, bingo, there it is. And I have looked around the couple of SEMs of this area on the Eastern Plateau, and I think basically using these Eastern Plateau SEMs, we can with a fair degree of certainty, say that how they're forming, where they're forming, and their life cycle. And we're going to combine that with some Rodinoff work early on, I think it was from 2000 and mid to late 2000s, and Savatimova. And I really need to work with both Rodinov and Savatimova to clarify and nail down the sort of and with Matsumoto, if at all possible, to really crystallize what is going on here. But what we are, in my view, doing is we are getting a deep insight into how ball lightning, what goes on within it. Now, obviously, if you've been looking through the photos of electronuclear collapse in the back of the Takaaki Matsumoto's book, you will see that depending on the elements you use, you will see the balls looking different. And of course, in those experiments, they were simple, they were quick. You can imagine that the level of compression in those experiments was or the level of coherence, or the level of coherent matter occupying the same space-time may not have been as high as is achieved in some other systems where you are pumping it for a lot longer period of time. For instance, in ultrasonic systems driven to the max, like in Suhas Ralkar's experiments, where he put titanium into his fuel mix because it's hard, and he thought that would actually cause the nickel and other he put tungsten in because he said that was hard and heavy, and he thought that would mill the larger grains of titanium and the larger grains of nickel down to his target of 5 microns. And he was absolutely shocked to find that after the 200 hours or so of ultrasonic processing, there was 0 tungsten observable. And we've observed how tungsten in many other systems can appear to disappear. But it only happens after a period of time. And so these systems, they can appear to do nothing, and then they do everything. There is a critical threshold that you go over, and the coherent matter, and it's actually detailed in Matsumoto's book. It kind of starts to interlink in a way that you can imagine Cooper pairs would do in a superconducting material, but on a much more intense scale, and it starts to dishevel and deconstruct the solid matter. And so just to leave a tidbit out there, and I will cue this up at the end, I also looked at the Hutchison knee sample on the SEM and the area within the triangle, and I also went to Scotland in summer, in July last year, to visit with one of the major collectors of John's work. And I have microscopy, not scanning electron microscopy, images of the knife that sank into an aluminium block. And with the learning that we will go through tonight, I believe we can fairly conclusively say how that occurred. It is in line with my previous discussions on the matter, but now we can actually physically recognize the active structures that are doing the work, and the zone over which they influence the material around them, and the signature that will be so clear, if it isn't already, of these light elements, particularly carbon, that are synthesized in the interaction area. Okay, so really, I think I gave myself 10 years to do this. My vision in my before I was 10 gave me in my 40s to do this, and I think really it's one thing to know something may be possible and it's a bit of a mystery. It's another one to see physically these things on camera, which John showed. It's another thing to potentially have a mechanism which various people that we've spoken about over the years has contributed to. But I think we are approaching a time that with more repetition and replication and establishing the parameters, although I think we can do this at will and at any time, producing these structures. And it is relatively simple when you understand the concept. I think that a whole world of opportunity will open up. And so the one obviously that I'm focused on is fixing radiation and remediation of nuclear waste. And in those using those technologies, we can move away from undesirable, damaging technologies like the production of solar panels, the placement of wind turbines, the flooding of large amounts of prime forest for hydroelectric systems, the use of so-called fossil fuels like carbon-based fuels in the case of coal, and the possibly abiotic synthesized, as I talked about in my previous video, now that we have an understanding of how that can occur, gas and oil from deep in the earth. And we can move to a system where if we need to up the level of carbon dioxide, we can use that. But I think it's better in pharmaceuticals and producing plastics and chemicals, feedstocks, and I also think it's very, very important for fertilizer. And I think the hydrocarbons that are there should be focused on those uses, and we could move to a largely nuclear world, which would free us from all of the destruction of the environment in many ways, because we know we'll be able to do it safely and in small units that will be easy to deal with if there is any rare problem occurring. And that should give us several hundred years easily, in my view, of clean energy, and we can move to understand in those hundreds of years how we can use this very same technology to yield direct energy. And there are already clues out there as to do that. I think we can do the PAP system, which is, in my view, exactly the same, but we have to protect against reactor failure, and that I've argued how you would do that. We can, and that gives you intense mechanical action, and also EMPs that can be gathered for direct electrical generation. I think that's probably the twofer that will win the day. But if you want a direct electrical generation, I think the Solin early 2000 patents, which David Boutelier has taken the lead on moving the investigation forward on that. We have that option, but we also have a partner who's developed a sparker and has a good understanding of how the PAP engine worked and wants it to be openly researched. So we have options now for facilitating the wide uptake of nuclear, I believe. And I think at the end of this presentation, or working through these slides, I think it will become clearer. And I think that we have options for both mechanical and direct electrical generation already available to us. But I think, like I say, we could have a window of as much as maybe 300 years to ensure that this technology can be deployed safely. But it is all around us. It is ubiquitous, as Ken Shoulders said. It's in us and without us. And so we shouldn't fear it. But it does manipulate matter. And without a doubt, there are people out there that believe they've had thermal melting when it's not been thermal melting. You get to a threshold and these things will consume anything that they come into interact with. There's nothing that can stop it. I've suggested using not ionic ceramics, refractory ceramics, but covalent ceramics like boron nitride in the past. And the people that are trying to pretend this doesn't exist have had more success by using covalent protection systems to contain their reactors. And there are other people coming on, and I will talk about some recent announcements in a separate video, but they're early on their journey of understanding how this form of matter can interact with ordinary matter and render dishevelment or just destruction, wanton destruction. And it surprises me, given the early advances by people like Bostic and Wheeler in the 1940s and 1950s through to the 1960s, that this hasn't been developed sooner. Obviously, the most easy thing that can be made from it is things that damage other things, and it's almost certain, as I've said, since 2017 that has been done. I don't know whether they got further than that, but I think really recognizing what this can do and how it can benefit humans immediately and in the long term is something that we need to get into the public sphere and consciousness. And having an experiment or series of experiments that makes it trivial to see the birth and death of these structures and what they can do, I think is going to be fundamental to changing the minds of people that are sitting on the fence or have never seen the fence to sit on it. And so there we go. That's my little spiel. So, okay. So I'm going to switch over to a little bit of my journey into how we got here. And I think since Tesla was meant to create ball lightning, he's known for meant to be one of the first or one of the only people in history that has been able to create ball lightning at will. I think ball lightning obviously was the thing that we should be focusing on, and I don't think it's any coincidence that the Russians called their meetings on cold nuclear transmutation they added "and ball lightning" onto the end of that, and it's always a discussion at their annual conferences. So I don't know why it wasn't recognized within the cold fusion field. I know Takaaki Matsumoto gave this book at ICCF 7, I think it was, or certainly materials from it at ICCF 7, but it really wasn't taken seriously, or it was, as I've argued in the past, deliberately pushed to one side. And that's a huge loss because we could be 25 years ahead of where we are now had great minds or even just capable tinkerers been bothered to look at these systems. But we are where we are, and we got here, and this is just how it is. It's just a shame that so many people have suffered because of resource wars, where I believe those were completely unnecessary. So we need to put an end to that, and not with the usual nonsense that everyone seems to bleat on about. This is a real tool to do that. What I can say, and you'll see in what I'm going to share with you tonight, that there are the Russians took his work very, very seriously. And the first paper that I will share tonight, I think, is one by Rodionov and Savatimova, and you'll see why I'm saying that they took his work seriously. Okay, so flipping over, this is my blog from well more than 3 years ago now, and it is UFOs over Hessdalen, Norway explained, ball lightning and low-energy nuclear reactions. Okay, so for those that don't know, Hessdalen in Norway is this particular mine-rich area that has a lot of quartz, and it has a lot of things like copper in it, and that will come back when we refer to Matsumoto's work and why he chose copper. And it produces a very regular array of ball lightning events, so much so that they have a watchtower there that does automatic recording, and there's been long-term studies of this there. And for me, the image that struck me as being very important and impactful is this one here, which I've given the source. Some of these sources may not exist, but I think I captured the sources at the time. And that is the important thing to do with the internet. If you see something and you think it's important, capture it. Don't rely on the fact that it's going to be there in the future. Anyway, so we have a ball lightning that's coming in with a spiral path, and its spiral having hit a tree over here, according to the person that made the recording. And it hits another tree top here, and it changes its structure moving over here. And this looked almost identical to strange radiation tracks, and we've seen the same kind of thing. So this for me was pretty much all I needed to see to connect the two. And you can go and have a look at this blog. It's very, very detailed. There's videos surrounding it in different sections and so forth. And I talk about the fact that the guy that was working who ran the United States Naval Research Laboratory, the NRL, Dr. Graham Hubler, he in 2000, and I think it was in 2000, in 2000 or early 2001, I think it was in 2000 when the Abrahamson-Dennis theory came out. He was asked by the BBC out of the blue, what do you think of this theory? And it's like, of all the people in the world, why did they ask him? And he said, yeah, this explains some things, but not everything, and so on. Anyway, the reality was that around later in the 2000s, there was this presentation, I think, on 60 Minutes about cold fusion, and this led to a philanthropic donation to the University of Missouri to the Sidney Kimmel Institute of Nuclear Renaissance, Skinner, and a lot of the current leading people in the field of LENR were brought into that. But when they looked for someone to bring in to run this project, it was this Dr. Graham Hubler, and I've met him personally, and he's a very nice and pleasant individual. However, in ICCF 23, he gave a presentation which was basically saying that EVOs are just Coulombic explosions, and I respectfully disagree. And this, for me, was straight out and out disinformation, and I would, encourage him to look at the work that shows that it isn't just Coulombic explosion. Though what I will say is that if he looked at the work looking into ectons by George Messias, who actually technically discovered the EVO a little bit before Ken Shoulders, but didn't actually publish it in the West until the mid-90s. He says that you get an energy concentration on a surface feature, and this leads to an explosion. And if you can imagine, the explosion is when everything gets to a point where it can't sustain itself anymore, and you have an explosion. But there's a critical point, and at that critical point you can imagine that everything is at the same energy. So there's a chance for coherent matter to form in these events. And I believe that's essentially what's going on. And so I think it's a little bit disingenuous what was going on. And it may be that he doesn't understand. And it may be that for some random reason, the BBC, when this Abrahamson-Dennis theory came out, that they randomly chose this person out of all the people on Earth. But he did say in the BBC article that the US Navy had been very, very interested for a very long time on how ball lightning works. So the military definitely took this seriously. And anyway, moving on, the Italian researchers, and I talk about this in this blog, they had gone to where a ball lightning in Hessdalen had struck the ground, and they analysed the the ground sample, and they had seen this. And I recognise this because I had seen one of these iron-rich crenellated spheres long before in my experiments on the supernova, in fact the nova reactor, and this was in 2016, in the summer of 2016, and you can see all these spheres in here, and they are crenellated, and you can see the crenellations here, but it's not so clear, but this is 500 microns, so the big ball here is about 500 microns, and bear that in mind when we look at some other things moving forward. But a lot of these smaller balls are of the class that they found in the Hessdalen ball lightning, and in fact this structure is almost identical diameter and identical morphology to the one that I showed you on the wall behind me from the Vega Valley, and the first large one. In fact, it's the second one we found in the valley, but it is this one of this size has the same kind of structure. I mean, obviously we've seen a lot more of those since. There were these magnetic balls coming out of the quartz outer sheath of the Lion 2 reactor. So the reactor is sitting inside here in its chamber, and it came through, and you can imagine it. It came through the reactor wall and through the copper oxide, and went through the quartz, and it came out and produced these magnetized spheres, and it went blump, blump, blump. And so it could be that the payload of coherent matter in there, for instance, a bosonic isotope of iron, could have just instanced. It's like instancing in 3D animation, if you don't know what I'm talking about. This is where you have a model for how something will be made, and it drops the instance down of that. It's just kind of dumping some of its coherent matter. So like you've got large numbers of atoms of iron whose wave function are overlapping, and when it gets dumped, they get dumped in like it's one part of it, one part of the matter that it is shielding within it, its mass is shielding, and it just blum blum blum. And I believe that you see this in the crop circle and so forth. Anyway, so this is the structure here. This was later in 2016 by a researcher on the Polish border here in Eastern Europe called Me356, and he acquired an SEM and he found this. And because we know this is carbon and so forth, this is likely, I believe, to be, I think it's likely to be iron here. But it has a very, very similar structure, this very spherical and crenellated structure with these bands. Okay, so that's that. And then John Hutchison, actually, for the Electric Spacecraft Journal in 1993, shared the ball lightning generator that he had produced. And this is the circuit that was used there, which I got permission to share. And there were transmutation, and we'll see more examples of transmutation, I'm sure, in Hutchison samples. And I can say, actually, that some of the major collectors have reconfirmed their offer, and some of the samples are being prepared for analysis in the coming period. Anyway, so there we go. That's and I talk about different technologies that clearly will be using that, and so that is that. Then we have the ball burn sample. I've talked about that a lot, but on this blog post here, Ultra Ball Lightning and Coherent Nuclear Transmutation, I shared the first how should we put this? The first spheres that were produced by Alan Goldwater, and he ran. I was using thin aluminium, and there were these structures forming, and I looked at them under the microscope. Anyway, it came from Alan Cusk, was the first person to try the experiment with aluminium foil. I said, go away and try different metals. Obviously, aluminium foil is the most easy to access. He did that first, and then I tried it and replicated his findings, but with a lot more fidelity. And then that inspired David Boutillier to look at it. And he thought, well, let's put a magnet in there, and he found that the cones seemed to be magnetic. And so I hypothesized that if this is making coherent matter, it would produce these iron-rich crenellated spheres. And therefore, I asked Alan Goldwater, because he had all the relevant equipment, could he go and do it? But could he use thicker aluminium? Because I don't believe mine would do it, because my aluminium was so thin, it couldn't run for more than about 180 seconds before the whole lot is mashed up. And he ran his experiment for just under 1,000 seconds, I believe. Maybe I've got it here. I don't know if I've got it here. But anyway, he ran a magnet around, and he found a whole host of these iron-rich crenellated microspheres. And you can see that this one is 40 something microns across, so this is bigger even than the ones that we observed in the Vega Valley. And you note on the outside, it looks like I love this one, it's like a little earth. But on the outside, you have carbon and silicon. And this is important because these are the elements you typically get synthesized in Lena, quite a lot of. And obviously the iron itself. And we're going to come to various authors that have suggested why that might happen. Okay, so there's the iron ball, very, very isolated. And we've seen a bit of that earlier today. Okay, so this is 10, 20, 30 something micron across, and you'll notice that on this 4 micron scale here, and we're going to see this repeating measurement all over the place, you have these little sections here, and they are of the order of 1 micron or less. Okay, and you know, in this one you could argue it looks like they're being even compressed more. So that's what we're seeing. And when you look at these under the SEM on the surface here, it's predominantly carbon, oxygen, and iron. Okay. Again here, iron. And this is atomic concentration. Obviously, iron is a lot heavier than carbon, a lot more nucleons in there, so it's not necessarily representative of the mass. And the other thing is about this, it's actually in water. So the idea that you would have a lot of oxygen on there and so forth is unsurprising. Okay, so you can see how it looks even smoother. And this, again, this is this, I don't know, is this the, how wide is that? It's 10, 20, 35 something, maybe 40 microns. So these are quite large structures. Okay. And here's one, and you will have seen some of these before, but you can see how it has this carbon film, this silicon carbon film wrapped around it. Okay. And what I want to draw your attention to on this one actually is the fact that this is almost a loop. This looks like a loop. This looks like a loop. This looks like a kind of loop, but it's got 1, 2, 3, 4 sections to it. This is a loop with a hole in it. 1, 2, 3, 4 sections to it. And so you've got another one here. 1, 2, 3, 4, 5, 6, 7, 8 maybe. There's another loop here. Okay. So I think at this stage, I want to draw your attention to something in Matsumoto's book. Before I do, if you can imagine this very large ball or one slightly larger, I hypothesized that this is a section from a ball. Now, this is 40 microns, so you can imagine this folded in so that you have, like, there's a triangular section here. Now, if there's many of these have a triangular point on them. So like there's definitely a sort of triangular structure up to maybe this point and down there. And you will have seen this on some of the balls that I shared earlier today from the recording earlier in the week. So if you can imagine this and it ripped down this triangle section, okay, you would end up unwrapping the ball and you would end up with a potential section like this. And I believe, and I said to Alan at the time, and I said, you can actually see here in the note, could this be part of an unwrapped sphere that was partially hollow? It appears to have 3 types of structures on its thickness. One that is amorphous in the center. This amorphous center here, so maybe I can zoom in. This amorphous here, it's completely amorphous in the center. One on the underside that may look like the outside. So I'm speculating that this outside section looks like the segments that make up this. Okay, and looks like the outside of the sphere is examined but cannot be sure, and an inside that is a cellular structure. So there's a kind of like cellular structure in this, which may or may not be clear to you. If we go in, maybe that's clear to you. There's kind of like the cellular structure here. So this might be the tail end of these, and this I've kind of argued that this is kind of like, this is the inside part of the double layer, and this is the fuzzy part of the double layer. But this is where all the coherent matter would be. And you can see here that on the inside layer, you've got these very, very high atomic concentrations of iron. So if you look at the outside again, the atomic concentration is 14, 16, 20, 24. But if you look on the inside of that, you have 40, 48, and so on. So there are some 26s down here, but the first 3 spots that he's got on here are higher concentration than you see on the outside. Okay, so I believe that this is an unwrapped sphere, and I think you're going to see evidence of these kind of things going on. And then I want to dig up Matsumoto's book. So if everyone's downloaded their copy, you will be able to come along on this discussion with me a little bit easier. So I think what we will do is we will look at page 134, observation of gravity decays of multiple neutron nuclei during cold fusion. And bearing in mind this was submitted July the 12th, 1991, and at this time he thought it was just multiple neutron nuclei, but he subsequently said that this is like every element you can possibly imagine can go in and come out, and so there we go. So right, so I'm going to pull that up, and then we can have a look at those images. So give me a second here. Has anyone got any questions at this stage? Hi WP for Truth. Hi Corky. Hi Artifact. Hi Gordon. Hi Kim, my lovely wife. Hi everyone. Thank you for joining us today. Okay, so I'm going to go to page 135. Actually, maybe I'll do something a little bit before that. Actually, because there's something very important that. Now, did he do it before or was it after? I think it was after, actually. Yes, okay. So, okay, I actually think it's more important at this stage to go to pages 192 to 199. So 192 to 199. This was later thinking, so you have to see these things in order, okay? Right. So the first is these kind of star explosions, and we saw something very similar going on in the ultrasonically treated fuel for the Echo reactor by Suhas Rauka. And I mentioned that earlier, and that's very important because we saw these exact type of stars going on. And this is the explosion of the structure. And if you go and look in here, we have a ring coming out of this, and I believe that we're going to see something similar in the analysis we did earlier. You have a ring coming out here. You have a ring that's kind of maybe doing some interesting tumbling motions and so forth. So you can see an event that causes this detonation. But you can go and have a look at that because you can. Okay, so here's some other structures. And what are these? I believe that this is the hollow structure. And why do I think it's hollow? Well, later in the book, he shows the carbon coming out of the center of the hollow. Much later than I was doing this, in late 2020, I came across Matsumoto in 2018. But in 2020, late 2020, I came across the work of Solin. He says that the north and south soliton charges, they cluster and they form these structures, and the structures are hollow, and the nuclear reactions occur in those structures, and they can form tubes as well. Okay, but I believe that what you're looking at here in this particular image is the same kind of double layer and the thickness. And if you note, if we go in, sorry, I'm clicking on the wrong thing, so it's not zooming in. If you note, we've got, as we've just seen, we've got these little kernels on the outside here, and then we have this smoother area on the inside. See the smoother area? See the smoother area? And I'm saying that that is not too dissimilar to what we are seeing on this image, where we have the internal area, which is smooth, and then this little kernel on the outside. So congratulations to Takaaki Matsumoto for doing this. So yeah, you got this smooth area here. See it? Smooth. And then the little kernels on the outside. And I believe this is all coherent matter. This is the fuzzy bit that you see in our VEGA videos. And this is the the sort of the event horizon sort of bit on the inside here. And what you're seeing here is where the structure has gone in 50% into this material, and it's affected the material in the process. Okay. At the time, I think Matsumoto had a different explanation for it, but I think you'll see that that is what it is as we move forward. Here's another one. Again, you can see on the inside we have this fairly smooth area, and then this lumpiness on the outside. Okay. Down here, what have we got down here? Let's move down there. This might be too wetted together. Okay. What have we got over here? This is a group of them, so you can start to see how they cluster. Now we go to this page, and on this page we got 2 ring traces. Okay, and these are moving around. We've got a whole bunch here and over here. And then on this page we have there, and then it's kind of like 50% in the surface, and it moves along the surface. It moves along the surface. And note, on the outside, it's more solid. Its outside's more solid. And we've seen exactly the same thing. We have to say, my wife has sent me an encouraging message, so thank you to my darling wife. So if you look here, this is more solid, and we've seen this in the coherent matter traveling waves images that I captured from David Boutilier's work, where you saw this more solid outside here, and then it comes to a stop. So this is more transparent because you're only getting the leading edge going through, whereas on the side you're getting a constant, a larger area. So it's kind of like a Fresnel effect. Again, you've got the same kind of thing going on down here. And like I say, you can look at this all in your own time. Now it's all public and available. Okay, so you can see this is 50 microns. So this is kind of like the size of the balls that we were looking at up here. These kind of size balls. Yeah. But it's not in this collapsed wave function state. It's in the coherent matter dense state as it's doing this, and that's why it can travel through things and so forth. So he actually explains, and there's a kind of broken up one here and so on. He actually explains the process here. Now, bearing in mind this is subsequent to the previous work that I showed you. Okay, it's subsequent, but it is important to see his thinking growing, so he's saying that this sphere, and he calls it a rotating ring, but I actually think it's a sphere, and it comes down, it interacts with the surface, and it bounces and it bounces and it bounces, and I think it goes into the nuclear emulsion, but it only goes 50% of the way in, and we've seen this in many systems. So I think he's very close with what's going on here, and I think his structures here in his observations are very close to what we've observed, and it's in this explosive event that you see these things coming out, that you see these light white spots traveling away, and I believe that these are the clusters that are traveling through the water, and they are then interacting and leaving these traces outside of the reactor on witness materials. Okay, so I think that's what I need to say at this stage from that part of the book, and then I want to go back to his earlier section, which was what was I saying? Yes, pages 165. So thank you very much, Takaaki Matsumoto, Doctor, because you fearlessly shared this work, and had you not done, I would feel like you did, standing out on a limb, trying to make sense of what I'm seeing. So, okay, so it's on your shoulders, Matsumoto. Okay, so you can see there's something going on here with a dark splodge around it. Something going on here with a dark splodge around it. You'll see a lot of this. This one, we actually created or observed an almost identical one, in fact, in almost every way, scale, or everything, on the inside of the supernova reactor shell. Those are very much different things. Now, if you look at these structures, they start to look very much like what we've just seen. We have a ball It has maybe some crenellations, and you can imagine that as the coherent matter is coming through the plane, there is a kind of like imprint left on the plane as it does that. So you get a little bit of what's going on, and then you've got this layer with these lumpy bits on the outside. And if we actually look at a lot of these images he has here, we can see more of this. So not particularly so much on that one, but here you can see there's kind of these lumpy bits on the outside. And like I say, different materials behave in different ways. And was that 135? 135 is where I actually wanted to be. Okay, so 135 here. So so he's got these traces here, and you can imagine the scales down here are 50 microns, so all of these structures are within the ranges of the ones that we have synthesized in our experiments. And so let me go in here and I'll zoom in. So in this case, maybe it's a more pure structure. It's you know, some of the smaller ones that we've seen, they have less crenellations on the surface, and this would be like a very young structure with a nice coherent boundary. We're starting to get some segmentation here, and you can see, I don't know if you can see, but there are these segments here which look a lot like what we were observing. Unfortunately, there's some JPEG artifacting in there, and we worked very hard to ensure that that didn't occur. Here again, you can see that maybe there's some partial interaction as the object went through. You can see the lumpiness on the outside, and you can see the segmentation here. I believe that this is an interaction of a very similar coherent matter structure interacting with the surface. Okay. Again, on this one, it's clearer. The very defined segment. And this is the inside of the double layer, and these are the cells on the outside that we are witnessing, and this is something that's 50% through the surface. Again, you can see this smooth area here. So what am I referring to? I'm referring to this segment here. This is the smooth area, and these are the kernels on the outside. This is the smooth area, and these are the kernels on the outside. I mean, the degree of correlation between what we can repeatedly produce and what Matsumoto observed is really remarkable. Again, these are the lumps on the outside, and you are seeing the hollow core, and I believe that these blobs are where the object went into the surface of this witness material and interacted in those particular zones. Okay, and there's one down the bottom here, and again on this one you can actually see the crenellations. There you go, there's the crenellation there, and I don't know how big that one is. That one is I would say probably 10 microns or 15 microns or something, but that for me clearly has the crenellation. So in my view, we are witnessing the equivalent objects. So these are the kind of individual objects, and then later on, well, firstly, in the next page, you have something that is very, very pure and coherent. So again, you've got the hard layer on the inside and this wonderful outside, and this is huge. This is 50. This is wow. This is 200 or something microns across, and we saw something nearly identical in the Amasa gas interacting with the 10 yen coin, and we have a very clear impression of that kind of interaction. Okay. So on this one, we've got another couple. This one's distorted, so you can this feeds into what we'll be discussing a little bit later. But you can see that there's a little bit of distortion going on here, and that shows that when they are this pure structure, they can be like squished and squashed. Now here in these 50 micron traces, you can see there is a large number of subunits, and you can imagine that this is individual little ones and then coming to aggregate, or this might be a point of disintegration at the interaction with the surface. He has it over here with a different type of lighting, and you can see here that some of the spheres are kind of like more individualized and other ones are kind of like wetted together. And we witnessed this in the actual electrodes live in the videos that I've shared from both David and Henk, where you have these coherent matter structures wetting together. So this looks like either it's coming together or it's in the process of falling apart. It's like a snapshot in time. Maybe this whole structure was flying through this witness material at the point it was just falling apart. And so you can see how it's kind of wetted together. So it's almost like unwrapping the noodle from the outside of the tennis ball, if you can think of it like that. And here's a whole bunch of them, and these would be what Ken Shoulders might call a bead chain. So not only are they clustering together, they are the clusters have a field fall off, and they both attract and repel, like likes like. So whatever's there's a level of self-assembly here, and we witnessed the same kind of structure in a ring structure interacting with the quartz on the outside of one of the Lion reactors in a almost facsimile of one of these interactions of these structures in work from Ken Shoulders. Okay, and there are other ones here. This is a very famous one because this is Matsumoto's clearest representation of the spiraling traces that you can get. And you can imagine if something blew up down here and sent out a couple of segments of it, that then as these came around and spiraled around, they interacted with the surface, they would leave these spiraling traces. And this one's very, very important, and you'll see why. And I think this image probably for Savatimova and Rodionov was probably the most important image in cementing their theory. But you can imagine that you might think that this is a ring, and we will show examples of that in our analysis of the Vega Valley Eastern Plateau. But you can see that it actually has the lumps on the outside. So I would imagine that perhaps this was a sphere that interacted with the surface, and that a section of it, like a cap, split off and turned around. And I thought about this in a different way earlier, but you can imagine if this was part of a larger sphere and you did a cross-section and this like unwrapped and came round here, it would produce this structure. But anyway, you're going to see something very similar as we move forward. So thank you very much to Takaaki Matsumoto because your work is absolutely fundamental to understanding what we are seeing in the Vega Valley. Okay, so that's that. So I think this obviously was produced by Alan Goldwater in an ultrasonic system. And we have been showing ones produced in a sort of some way between ultrasonic and pure plasma, and that is in the work of Takaaki Matsumoto, which we've just been looking at. And the Vega, of course, is a pure plasma system, although you have water in there and so forth. Anyway, so you're going to see a lot more of this, but I have to draw attention to this image here. So this is carbonized film. I will note that the full scale on this is 200 microns, and this smaller scale here is actually 1 millimeter. But as this is self-similar, I don't think that's important in terms of getting across the message. So what we have up here on the top left is Matsumoto generation of carbonized film, and he, I think in this case, was a copper plate, and so that is lighter, and the carbon is showing up on the copper witness plate here. And you can see it has this kind of spirally churned, or rather sectioned, churned structure. And I believe the equivalent is being shown here, although it's a little bit more messy in what's going on. And then in this case, he's showing carbonized film containing iron. And maybe he was referring to this carbonized film, and if that's the case, I would suggest that probably this is an equivalent of that, or one of these where it's actually carbon, but maybe it has some iron in it. I don't know. But I do wonder, and I need to check with this, because down the bottom here, you have a sphere, and actually this scale is identical to this scale. So that is 100 microns, and this is 100 microns, and I ensured that that distance from there to the center point there is the same as that. And if you look at that sphere, which does have a little bit of geometry to it, if that is a sphere, it is largely identical to the range of sphere sizes that we are seeing on this particular sample, for instance, that one. Okay, and we're going to look at a lot of things of what's going on in there. Right, now I'm going to skip to the Rodionov and Sabatimova paper, and before I do that, I'm going to ask, is there any questions? Hi, son of Overbook. Yeah, David, a bit like the tungsten chop shop. It's kind of like a broken donut, but I don't think it is a broken donut. You will see broken donuts. You will see broken donuts. But in this case, I think it is actually a broken sphere. Anyway, we're going to see everything. And with the now I know, like, it's like when you see that first ball. You see that first ball in the Vega Valley. I knew that was important, and I couldn't wait to get back to the SEM, and bang, I found another one on the same session. And then after looking at that one, I realized there was another one in the shot, and that gave me the image that we have behind. But then that gave me confidence to look, and I did a ball search, and we could see even on the optical microscope that there were many other balls. So the next time you've seen those live sequences of me looking for balls. So we've seen plenty of balls, but then I got to think, what was clear on the interaction of HHO in the form of a maser gas, this very high quality dense HHO, in the interaction with the 10 yen coin, that where the main ball lightning occurs, there's so much going on that you can't separate the one action from another. It's all churned up. But the action which is interesting goes on the periphery zone, where you get things coming out. And in fact, Takaaki Matsumoto designed his experiment with the wire experiment such that his witness material was at a distance. And in fact, a number of his experiments were at a distance. And in fact, Shoulders did this. And I don't know why it took me so long to think of like that. But anyway, the point is that what you want is a fairly pure and unblemished surface, which is at a distance, that receives a much smaller statistical number of events, so that you can actually sort the wheat from the chaff, if you know what I mean. Find the needle in the haystack, because there's no haystack. The needle's just sitting there on the ground in front of the haystack. So that's what you want to be doing. And so that got me thinking, well, if there are all these balls, and I believe they're being made in that central channel, and we will see, and that is the case. That is what the case. So what you had is that you had a sheet of brass, and then on the sheet of brass there were two sheets of brass with a gap in between. Okay, and we'll talk about how I've talked about it in my previous video on something electric, about the various factors that played into why that was so good, and and so forth, and we'll recap those in a minute. But anyway, they're made in that central channel, and then some of them, or partial parts of them, burrowed their way in between the gaps between the two brass sheets, one on one side and one on the other. And we know this because the actual top pieces on there have the mirror image of the channels, like worms burrowing through oak wood on the other side. It's like if you actually cut a piece of oak that's had woodworm in there, and you cut the channels in half, you would see one on one side and the mirror on the other side. And so that's what you see. And so I'm imagining that ball lightning is coming out of that central channel, and it's eating its way down, and then it will come to its own demise. And we know that that's what's happened, because we saw a range over which it could travel, and then there was nothing beyond that point. So that, for me, I go, oh my god, there must be balls all over that area, so let's go and have a look. And so I decided to spend most of that expensive session this week looking, and there's actually a couple more videos to share, but I think we got the main ones out there really to tell this story. And it's really what's on those 8K images that I captured that tell a bit more. Okay, anyway, moving back. So here's one of these moments in time where you go and look at the references of a document like this. Unusual structures on the material surfaces irradiated by low energy ions. This is by B. Rodinoff, Moscow Engineering and Physical Institute, State University, Russia, and I. Savatimova, Federal State Unitarian Enterprise Scientific Research Institute in Russia also. Okay, so I'm going to go and have a look at the references in this before we go through and look at the paper. And I've actually reviewed this paper in one of the videos that I linked to in the blog today in the past. But here we go. The number one reference of these authors is T. Matsumoto, Steps to the Discovery of Electronuclear Collapse. This very book is their number one reference. Okay? Someone was listening, Dr. Takaaki Matsumoto. They were really listening. Savatimova, one of the authors. Oh, there we go. Mikhail Solin. Well, there we go. From 2004. I'd love to see this paper. Oroitskev. Leonid. Bogdanovich. Oh, hello. Who we got here? Is this John Archibald Wheeler? And Richard Feynman? From 1949? Right there. The top references. Okay? So let's go back to the top. Some unusual structures on the surface of metals and films, various X-ray films and nuclear emulsions caused by exposure to bombardment by low-energy ions in glow discharge plasma in electrolysis and other low-energy processes when energy of particles doesn't exceed several kiloelectron volts have been found. The mechanism and model of the strange track formations and explanation of their structure change are suggested. Introduction. For a number of years in various laboratories of the world, physicists discover strange tracks, which we call traces, whereas the objects that cause them are termed as tracers, 1 to 5. Okay, so those are the first 5 references. Number 1 being Takaaki Matsumoto, you've got Leonid Oroitskev in there, you've got Bogdanovich, etc. The traces, as a rule, are characterized by a microscopic width, usually about 10 micrometers. And you'll see that number come up a lot. But their length is presumably unlimited, millimeters and more. Sometimes the traces look like a repeated pattern, similar to the tread design of a motorcar tyre or a necklace. Sometimes the pattern forms a continuous line or group of parallel lines, differing from the standard tracks left by heavy charged particles in nuclear photoemulsions by their angularity or enormous length, up to centimeters. Occasional flaws of the samples containing traces on the polished surface of metals or in photoemulsions do not explain the connected occurrence of the traces at the places of local energy generation. Electrical discharges, particle accelerator targets, and the areas of natural disasters or technogenic ones, which are caused by human activity. This feature of the phenomena is in question may be used to predict or to avoid the technogenic disasters. For example, the search of traces can help in analysing the causes of the Chernobyl catastrophe. We're going to look at Chernobyl. We're going to look at the other accident that occurred in Russia prior to Chernobyl and Fukushima. I believe all of these things were caused by exotic vacuum objects or charge clusters, however which way you look at it. And I'm translating some Russian work with permission of the author that goes into that in detail. Anyway, experimental results and discussion. And the reason I'm saying that is we do have a nuclear future. We do have a way to protect. But we absolutely are completely irresponsible in not educating the people making the nuclear reactors, the people funding the nuclear reactors, oh, that's you, and the politicians that are the brokers in between those two actions. We will be irresponsible as humans to not wake the world up to what caused these accidents, really what caused these accidents. And in that light, I'm going to be writing a paper with another author based on the discovery of highly radioactive particles which look like they were EVO core clusters and that caused the explosion in Fukushima. Now, I believe all those major nuclear disasters are caused by that. This must be made public, and by making this public, The whole thing gets made public. Okay. Right. Experimental results and discussion. We observed unusual structures on the surface of metals after glow discharge exposure, and on the films, various X-ray films, nuclear emulsions and others, placed both on the inside and the outside of the glow discharge chamber. The similar track formations with periodical repeating structure were found on the nuclear emulsion films after neutron generator exposure. Such track structures, as demonstrated in figures 1 to 3, regular structures, spirals, chains of voids, and others, need the comprehensible explanation from the viewpoint of material science and demand special physical interpretation. However, the classical approach to the study of physical phenomena requires not only substantiation of the principal possibility of the process in question, but also its detailed description, including illustrative examples. The latter may become possible on the basis of model of filiform, thread-like filament matter, i.e. fluxes. Some components of the flux theory will be discussed below in application to the problem under discussion. Along with traces in metals to a depth of 1 to 2 centimeters, changes in physical and chemical properties of underlying layers from the viewpoint of their composition and structure are observed. Under the surface of previously monolithic sample, some microtunnels and holes appear. Figures 1 to 4. On the surface of the samples examined before the exposure, without any distinctive of the samples examined before the exposure without any distinctive properties. Not only traces, but also some microscopic structures, films, hollow spheres, and cylinders. Threads, spirals, complex spherical and cylindrical forms looking like cabbages or sausages were discovered after the exposure to low energetic electrons, ions, or ultrasound action. Sometimes these structures remind one of bacteria or a colony of bacteria, which we have just shown, I think, from Matsumoto, which may glow, fluoresce in the dark. These objects move randomly or appear on the surface or plunge back into the depth of previously monolithic material. This activity of live bacteria objects may continue for weeks after the energetic influence, after it has been finished. And this is talking about Bogdanovich's work, which was only really published in the most serious sense in I think it was 2019 May. Each of these objects is unusual in the shape, surface structure, and the chemical composition. The chemical composition of these formations is sharply distinguished from the composition of the basic material on which these formations had arisen. Tables to figure 4 with chemical composition. We shall take into account that all these objects have been obtained under conditions of low energy particles influence, when the nuclear processes in materials from the traditional point of view couldn't exist. Therefore, at present, there is no comprehensible hypothesis for the formation of such structures from the impurities. We shall also take into account that the majority of the chemical elements forming unusual structures were not present in the initial material and in the composition of the surrounding medium, or in the constructive details of the experiment installation, so in the reactor. So we've seen these traces before, and thus the shape, structure, and composition of unusual objects demand special explanation, probably based on new physical concept. This unusual concept, as well as other possible practical application, requires further examination of unusual structures. So this is melting of a bubble. These are spiral tracks. These are cylindroid-like sausage tracks. These are more spiral tracks with a movement. This is one very similar to the one we saw on the material exposed to the at a distance on a PET bottle from Suhas Ralkar's fuel. And we've all seen the M&M tracks, and there's another one similar to above. Okay, periodic tracks. Okay. And in these periodic tracks, it says, is the result of fast neutron interaction with carbon nuclei with 3 alpha particle formation, 12 carbon. So this is the triple track here that they're talking about. This is a fast neutron interaction. Okay. Okay. So, explanation and possible mechanism. We can offer 2 approaches to the explanation of the formation of such unusual structures, integrated and differential approaches. The integrated approach, in the view of the long-range action concept, in which development of Feynman and Vladimirov and others participated in the second half of the 20th century. Formation of the complex objects capable of leaving observable traces with complex structures. Traces can occur instantly and at once. As from experimental researchers at the end of the 20th century, the traditional concept of philosophical reductionism, occurrence of big objects from small parts, in many cases showed physically insolvent. Okay. Anyway, and they're showing some transmutation on the elements here. You can go and have a look at this in the own time. The vivid example of this was the detection of a fractional quantum effect of Hall, the Nobel Prize of 1998, and his theoretical interpretation by Robert Laughlin. The observable fractional charge of current carriers in semiconductors appears as a result of certain condition of all semiconductors. Self-similarity, as direct consequence of long-range action, explains any transformations of substance as quantum transitions in the universe. Right. Now, I really need you to pay attention at this bit here. So, occurrence of observable forms of life in the universe, or complex structures of unusual chemical compounds such as traces on the surface of electrodes bombarded by ions, are the next state of the universe. Self-similarity of objects of the universe could explain the process, but does not allow considering the dynamics of such quantum transitions. The differential approach. It is based on a stage-by-stage formation of complex objects from more simple ones, and allows considering dynamics of transitions from simple to complex. I'm kind of agreeing with this already, and you'll see why later. This second approach from reductionism position is traditional methodology, but as against the first approach, in our case, it does not allow to skip through the basic difficulties. The possibility of cold transmutation of atomic nucleus is not simple to explain from this position. We suggest overcoming these difficulties on the basis of consideration of a new hypothetical filamentary structure of matter. The basis of using such extravagant assumption is the astrophysical data on the presence in the cosmos of so-called dark matter, which makes the most part of the mass of the universe. The dark matter can have filamentary structure. If diameter of filament is close to the diameter of atomic nucleus, they will easily pass through any dense substance of usual nuclear molecular structure, through any solids, planets, or stars. In the author's model, such filaments, fluxes, can be cylindrical atoms. The nucleus of such cylindrical atom can represent a quark-gluon filament stabilized by a quanta of magnetic flux and an electronic shell. An electronic Bose liquid with properties of superfluidity and superconductivity. The diameter of the flux of the electronic shell, according to the calculations, is in this paper. Fluxes can create an invisible grid, like a Itonic mesh, maybe, which wrap around not only far cosmos, but also all our planet, penetrating all our bodies, solids existing on Earth, including us with you, and influencing them in various ways. Interaction of invisible fluxes with usual nuclear molecular substance could be in various ways. The huge gradient of a magnetic field promotes an attraction to magnetic poles of particles with non-zero magnetic dipole moment. Electrons, protons, neutrons, many atomic nuclei, atoms and molecules, ions, which can enter into nuclear interaction. It's this magnetic dipole moment that I believe is important for instance, something like protons, and particularly for something like fluorine, and why I found it interesting as a LENR fuel in PTFE, in the experiments which we did in Japan. Elementary calculation shows that frequency of nuclear processes on magnetic poles of hypothetical filaments, fluxes, should reach 10 to the 14 to the 15 second minus 1, which enables evolution of an output power of 100 watts. The approximate rough guess is given below. Then they do the calculation. We're going to skip the calculation, okay? You can go and have a look at that in your own time. Okay? Nuclear reactions can also go on lateral surface of fluxes in an electronic Bose liquid. This is a coherent matter. Electronic Bose liquid. This would be fluidized electrons, which shields the electric charge of nuclei. Do you know the hydrogen metal project funded by the EU, are doing extraordinarily in-depth experiments to try and create slightly higher levels of electronic shielding in metal samples. This just does it. It just does it. Okay. All right. In the end, plenty of atomic nuclei in the usual nuclear molecular substance forming lengthways ensembles of fluxes, quanta with cross sizes of about 100 microns, can interact simultaneously. So what they're saying is that matter that comes within this 100 micron area basically can simultaneously interact in this highly shielding environment for electronic nuclei. Thus, the problem of cold nuclear fusion and nuclear transmutations in the fluxes model is authorized by three ways. Enabled, I would say. Transformation of the atomic nuclei on magnetic poles, ends of the fluxes, in electronic liquid on a lateral surface, fluxes, and in multi-nuclear reactions in associates of fluxes, nuclear ensembles. Okay. So basically, they're saying you might have a thing that goes through a material, and then on this end and on this end, you can have nuclear reactions occurring, right? This would be, in my view, the wormhole, the structure between a black hole and a white hole, according to the Matsumoto theory, which is their #1 reference. This wormhole, this flux, which would explain the north and south magnetic pole structures that we found on the outside crust of the Lion reactor, the Lion 1 reactor. Okay, and then they go on. And then there's stuff on the outside and outside of clusters. Okay, due to non-conservation of spatial parity in E-capture in the powerful magnetic field of fluxes, the main flow of a rising neutrino is directed against the force lines of the magnetic flow. As the result of E-capture, the filaments of neutrino at the northern magnetic pole create jet traction, which pulls the filament after the North Pole, like a locomotive pulling its cars. I believe that this is the reason you see this kind of beam coming out, or this phantom beam coming out of the clusters in the experiments of VEGA by Butelier. You see these interactions where something is coming along here, and this will actually start to be deflected by whatever's coming out of the front of this thing before it even gets there. It's like, basically, I tried to think of what was going on. And if we're saying that relic neutrinos are the cause of gravity in a push gravity model, then if you are able to suck them into a structure, then you basically have an intense gravitational well, which would influence another one that has another one in front of it. It would already interact with it. So what they're describing here meshes beautifully with the physical observations observed in VEGA reactors. Absolutely, those extreme interactions that we observed. What they're talking about here fits with that, the extreme magnetic fluxes. Okay. Like a locomotive pulling its cars. At the southern magnetic pole, force of reaction of a neutrino pushes, compresses the filament because of which unstable movement of south pole of the filament is possible. So this is what I'm saying. One of the poles ends up being a maker and the other one ends up being a breaker. Okay, and it's one or the other. Okay. Due to output power of capacity during the nucleus transmutations, a part of the new nucleus is formed on fluxes, in particular nucleus with zero spin and hence with zero magnetic dipole moment. Okay, so what is that telling us? Well, they're saying zero spin and zero magnetic pole. Sorry, well, let me go back. It's zero spin and hence with zero magnetic dipole moment. They are in particular, not exclusively, but in particular. So let's go to the Philip Power programmed Martin Fleischmann Memorial Project reaction calculator. And this is not part of what was provided by our good friend Alexander Parkhomov. This is something that I asked Philip Power to put in. And this is extra elemental data. And if we look at hydrogen here, it has a... I don't think I've got a spin on there, have I? But if we go to helium, and yes, sorry, hydrogen here, if it goes, is it going to update? Is it going to update? Oh dear. Come on. I've got an issue with my internet. Can you see me? Okay. So, okay, anyway, it's given me the helium data, and that's what I wanted. There's always been a question in LENR why the branching ratios for deuterium-deuterium fusion in LENR do not favour or accurately reflect the amount of helium-3 that should be produced if it was normal particle-particle interaction fusion. And you tend to get helium-4. Well, then this theory that is proposed by Rodionov and Savatimova shows you that your helium-3 has a spin of a half plus, and helium-4 is a null spin. And if this was working, I could show you that things like carbon, is it going to give me carbon? I don't know if it's going to give me carbon. Is it going to give me carbon? What I can tell you is carbon-12 and carbon... is it carbon-12? Carbon-12 has no spin. And oxygen-16 has no spin. And if we go down to other subjects like... which typically get synthesized, silicon-28 and silicon-30 don't have any spin, and calcium-40 don't have any spin. So based on that, I think they are fairly accurate. Okay. Yeah, you can see me. Great. Thanks for confirming that. Okay. So I'm going to go back to their paper. Right. So now this is interesting here. They should scatter, forming a hot shell of these new nuclei near Flux's filament, which are inside dense nuclear molecular substance. Due to melting and evaporation of nuclear molecular substance with its subsequent condensation on cold parts of the sample, nuclear active fluxes leave their complex structured traces both on the surface and inside samples in which they are formed. The nuclear active fluxes are complex flux objects. We name them such an object tracer and can move along trace trajectory in the substance. Okay, so I'm going to go back to here. And I'm going to show you on the blog for today a couple of examples. So you've got material around the outside, material around the outside, but more clearly you have this deposition on the surface. So this is your main structure. You have this inner skin. These are your little kernels on the outside. You're seeing 50% cut through. This is the one observed on the inside of the supernova reactor. And this is it, scale for scale, aligned with the one from 1993 in the cold fusion experiments with ordinary water and thin nickel foil in Matsumoto. Okay, so he has again this inner boundary and then these kernels on the outside, inner boundary, kernels on the outside. Okay. And this is the color one. And so this, I believe, is the carbon predominantly that's deposited down. And you can see here we've got a trace coming in from this angle. And this is very similar to the one that is in Matsumoto's paper, which we are... am I talking about it here? This one here. Okay. So at the end of the video today, I said that potentially these structures could be where one of these things, like, it kind of touched down on the surface. It didn't fully go in, and then it went away. But you're seeing these segments, and the segments are like the segments here. And this is the carbon deposit on the outside around here. So this is what they're talking about in that paper. And so it almost doesn't matter where you look. You see the same structure if you care to look. And so, yeah, this is the center bit touching the surface. This is the center bit touching the surface. You can see the bands between it, and maybe I can zoom in here. I'm looking at this under different lighting conditions from different angles, but you can see these segments here, okay? And in this case, the top of this and the bottom of this sphere have been squashed into this aluminium of the reactor chamber, but still you have this fall off here, okay? And you can see there's a 100 micrometer scale. This is a 100 micrometer scale. So the amount of spread of material around this is in the order of what they were talking about. Okay. All right. So let's go back to their paper. The filamentary tracer of the structure can leave a trace without moving at all. We've seen that. Or moving, for example, in the perpendicular direction to a line. In figure 5T, this is the top part of figure 5, the presumed mechanism of formation of the various shapes tracers is shown. The atom molecular quantum ensembles surrounding fluxes. So the flux here is this white bit, right? This is the atom molecular structure around the outside, and this is where you get the coherent matter forming, okay? Superfluid, superconducting electron ion Bose fluid condensate. Okay, the atom molecular quantum ensemble surrounding fluxes, the grey coloured cylinder in figure 5T. So these are the grey cylinders. Okay, blah blah blah. The atom molecular quantum ensemble surrounding fluxes, the grey coloured cylinder. So the atom molecular quantum ensemble. So this is a coherent condensate of material surrounding this flux. Okay, the grey colour bubble to the periphery of the ensemble, where the temperature of the ensemble substance is lower. The density of the atoms is higher, and probably of polynuclear reactions is the highest too. Such pushing out results in the bending of the flux like this, and atomic molecular ensemble surrounding it and interacting with it. So this bends and it bends and it bends into a loop, firstly into a U and then into a loop. Okay, such as pushing out, blah, 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 blah. And so you can see why I said that Matsumoto's this probably was one of the most significant things that were in their thinking. But I actually think that this is a sphere, and you're seeing a cap coming off, and it's the interaction. Okay. In turn, the bend of the ensemble with fluxes can lead to turning the ensemble with fluxes into a ring or a spiral. Okay. And so that's these ones. And so you end up with it winding itself into a sphere. Okay. Or a sphere or a torus. And then this is talking about how they interact with surfaces and how multiple ones that are inside each other can end up by producing bizarre traces. So let's note that sometimes geologists found such spirals of microscopic sizes, for example, of refractory tungsten inside various compact samples in rock in reality. Geologist Elena Matvieva found tungsten spirals inside 200,000-year-old age rock. Figure 6. And so I've talked about this before, and these are the tungsten spirals that they found in the rock. Okay, 200,000 years ago. Formation of more complicated bodies of cylindrical or spherical symmetry during warming up by nuclear reactions. Figure 5, bottom, F and G, here we go. It's also possible the formation of hollow cylinders and spheres. Hollow cylinders and spheres is possible as a result of oozed gases in the chemical and nuclear reactions and in environmental substances around the fluxes. Sometimes it is possible that such elementary processes create hollow quasi-sphere particles, blobs, and extensive hollow cylindroids on surfaces of metal sample. And that is A, B, and C. Blobs and cylindroids can be broken off on the surface or near the surface of the sample by internal pressure of gases contained in them, leaving in the local zones of metal surface the melt films formed near nuclear active fluxes. Helicoid atom molecular shells of nuclear active fluxes in projection to the flat surface of a sample frequently give the sign pass trajectory with changed composition of the basic material. Traces in 5 bottom, these traces. Okay. From known mathematical Fourier's theorem, it follows that the sum of sinusoids or cosinusoids with different amplitude and period can give a track of any shape, the geometrical pattern repeating periodically. This is what I did in my simulation, which I will do much more detailed simulation of what we observed physically going on in the experiments by Henk and David of VEGA, these coherent matter traveling waves. 100% I can stand by that. I believe they are coherent matter standing waves. Okay, traveling waves, coherent matter traveling waves. So they are a bit of one of these structures that's been blown off, and they are traveling. And they are, if they're a torus, they're spinning, and they're spinning around their own axis and a common axis if there's some other group there. Okay, such kinds of double spiral objects we found on X-ray film, blah, 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 blah. Okay. In our opinion, the origin of mysterious periodic patterns, chains, and more complex trajectories, figure 1 to 4, on the surface of the samples can be explained by such kind of processes. Thus, concentration of the fluxes earlier not participating in the process of nuclear interaction with the substance, but activated by electromagnetic and nuclear processes in various places of trace is possible. The secondary interaction of these fluxes can considerably complicate the trace figure. Especially the composite figure can arise from cooperative action, combined effect of several nuclear active fluxes, which form, for example, enclosed spirals. And from activation of earlier passive secondary tertiary fluxes. Anyway, we've shown them interacting with each other on video. Okay, we hope this further, blah, blah, blah. So I thank you to the authors here, Rodionov and I. Savatimova, because I think that they have really described a good detail. And it's just wonderful to see that their principal reference was that of Takaaki Matsumoto. Okay, so it's actually showing me the silicon here. So silicon, you can see 28 and 30 have no spin. If we go to the helium again, if it's going to show me quickly. Yeah, so helium-4, which anomalously gets produced in Lena, is no spin. Obviously, oxygen... Oxygen, where is it? Oh, it's now back to being slow. But anyway, oxygen 16. Nitrogen has spin, and that's probably why it's more of a fuel than it is a product. Okay, you know, two nitrogens goes to silicon, and there's other reactions like two nitrogens go to one proton and one aluminium 27. So one that I've talked about in the past. Now, before we go into the analysis of the SEM images, I will just show you this. This is scanning electron microscope view of an iron crystal on, I think it is dust from the moon. Okay, the largest crystal is 3 microns across, so I guess this is 3 microns across. And bear that in mind. This is maybe 2, and this is 1 microns across. Okay. And these are iron oxide crystals, and there's a wide variety of what iron oxide crystals look like. So I suspect that when the coherent... Oh, sorry, I lost that. When the coherent... Oh, it's lost my... No, there it is. Okay. So when the coherent matter comes out of this condensate and it regains its electrons and presents itself as ordinary matter, then it will form little crystals, and they won't be perfectly smooth. They will form like the crystal has to form, which is these blocky type structures. So hold that in mind. Right. Okay. And any questions before I go into look deep into the SEMs that we saw the other day, which you haven't seen what I've seen in these SEMs, which is rather exciting. So before we go into this, I just want to go over this paper. So essentially, I proposed, by looking at John Hutchison's materials way back when, that what was going on in John's samples here was similar to the D4D structures observed by in 1980 and by Bostic and Nardi, and this is in their paper. And you have, again, if you look at this, I don't know if it's clear, maybe I can get a higher resolution. I haven't got a higher resolution than that, but in this trace we see the hard inside area and this segmented outside area. I believe that this is the same thing that we observed. Okay, and then we saw on Hutchison samples, this is on Bostic and Nardi, and then we saw on Hutchison samples different tiers of something going on. So I thought that they might be organizing themselves into clusters of clusters, and you can see here a close-up on that. And where are we? So I built this structure up out of toroids, and then I believe that for them to fit in to the structure, the toroids had to be pinched. Okay, they had to be pinched. So on the outside, now the reason this has got 48 segments is because the large 1.6 millimeter structure on the Hutchison fracture sample, the MFMP Hutchison fracture sample, had 48 segments, it would appear, around the outside. And so that's why I did that. All I did was I said, when I'm doing this video, it doesn't need to be 48. It will be whatever is available to it. But anyway, you'll see why that's going to be interesting as we move forward. And then I said, like, you know, the subsections need to be pinched as well if they're going to go on to the next tier. And so you end up with a pinched structure here. So these are pinched and these are pinched and so forth, and this makes the big torus. So this is X, Y, and Z. But on the paper by Archibald Wheeler from 1954, he has his geons, and the geons, or geons I think he calls them. Where is it? Where's your geon? There we go. There's our geon. He says, regions of strong electric field strength in a simple toroidal geon of zero angular momentum. Okay, so this is like static, it's not moving, and it says 2 waves of equal strength run around the torus in opposite directions to produce a standing wave with electric fields strong in the regions indicated. So these have strong electric fields, and magnetic fields strong in the regions in between, in these areas here. Okay, the gravitational field created by this disturbance and required to hold the disturbance together is representable to a good approximation as a static and independent of azimuth. Okay, so I think what he's talking about here is this, the gravitational vector here. Okay, so you can see potentially that the gravity decay of material, as discussed by several authors, and on the cover of Matsumoto's book, which I thought I had behind me, but I can't see it right now, his 1990 book, it says gravity decay of quad neutrons, but actually he realized that it was decay of many nuclei simultaneously. And so from this analysis of John's work, I came to the conclusion that the structure looked a little bit like this, like that at the end. If I can show it, there. No, it's not going to show it. I'm going to try it at the beginning then. this structure here. Okay. So you've got pinched, pinched, pinched. Oh, this is not pinched because it doesn't need to be pinched. Okay. So bear this in mind. And like I say, this is 48 segments and this is 48 segments. But during my discussion in later videos, I said that, you know, you could have 4 segments or 3 segments in this section, and you could still have 48 segments in here, but then this could be like 5 segments, and it could be 5 segments or 10 segments. So, but you get the general idea. This was just built off John's particular material. Okay, so I'm going to pull up the analysis images now. I think you're going to be able to understand very precisely, I believe, hopefully by the end of this video, but if not in coming days, very clearly what has gone on in these to build these structures. Okay. So I guess the first image I just really want to talk a little bit more about is this one, which was the cover for this live presentation. And before I do that, I'm going to go back to the page in Matsumoto's book, which is relevant. That is in the end of that paper. Is it the end of that one? Was it the 1993 paper? Right, so 162. Everyone gets their Matsumoto book and goes to 162. Textbooks, guys. Oh dear. 162, 162, 162. Yeah, okay. So what I was speaking about in the part of the session that you saw earlier today was this, and you can see this trace here and the ball at the end of it, and I believe that you have something similar going on here, and different elements show different levels of structure. Now this one is a much smaller structure, and what we find is that when it's iron that is composing the Itonic cluster core, then it is typically, these are sort of 1 or so microns, half to 1 micron for each of the segments in here. But if you can imagine, it would be bigger, and there was some self-similarity going on, that you could end up, when this touches the surface, it influences these areas but not these areas so much, these areas but not these areas so much, so you end up with this structure. Okay, and around the outside it deposits the carbon, and this is because this is within the region of the iron rich electron condensate, as discussed by Rodionov and Savatimova. Okay, so this is the fuzzy area you see in our experiments in VEGA, in the live video experiments and stuff, if you go and look at the VEGA videos. And this is the kind of nearly the inside of the double there, and then the very much inside is that thing that we saw on the split thing. I believe all of these balls are hollow, and I'm reminded of in 2018 in Sochi, when I was sitting next to Anatoly Klimov, who's a senior researcher at the All Russian Federation Plasma Physics Institute. It was the day after the conference. I just happened to be there because of my flights and everything. And he was talking to someone. I joined him at the dinner table, and he actually switched to English, which he's very courteous to do. And he was complaining that he couldn't understand why the systems always tend to produce these hollow spheres. Well, there we go. And you'll see that is what they're doing, because in these sequence of images, we have everything we need to know that that is the case. So if you can imagine that this is touching down on the surface, I believe it will create something like this. And if you look at what I shared on my video, no, where is it? It's gone now. Where is it gone? Oh dear, I moved it. Give me a sec. So in this Evo 2, and I've got the image, the images for you, but I'll have to add it into the blog later. Here we have the, oh god, here we go again. Right, in this supernova Evo 2, we have the affected zone here. In fact, I will, oh yeah, I've got this structure here. It's something similar. You've got affected zone, but I have this showing the carbon deposit on the outside. It's not so clear here. This is the central area, and it has these segmentations. This is quartz, so likely I've not done the analysis, but I expect it's quartz. Or it could be carbon, but in a sort of diamond type structure. But you have this mark coming in of the deposited carbon, and this, interestingly, is 10 microns, by the way, just to let you know. In fact, maybe I will get that image from my resources here quick. If you give me a second. Is it there? Oh dear. Maybe I can't find it as quick as I liked. Well, just by the by, this was found on the palladium Amasa vibrator plate here. And this is another structure, and this is why I'm saying you maybe have less segments in certain structures, but I'm going to go back and nope, it's not there. I think this is on the indium exposed to Mauser vibrator plates, and you can see here this is the ball with the carbon on the outside, and this is the ball. This is 50, it's 100 microns across, so this is of the order of what they're talking about. And Matsumoto saw very, very similar structures. This is images from analysis of Hutchison samples, and you've got the smaller structures here and other structures. This is 40 microns across. Here's a bigger structure, and so on, that I was talking about earlier. This is from the side. You can actually see the pinch through the torus from the side. So that isn't what I wanted to show you. Maybe I can. I don't know whether I've got that easy to hand, or as rather easy as I wanted it. Oh, maybe I have. Is it here? Okay, yeah, okay. So, right, so here we go. This is the structure you saw in the background here. Under different lighting conditions. So you can see this field drop off here. This is the channel coming in. Different lighting conditions, the channel coming in as it cuts through the structure there. And then I actually have a close-up here. You can see these sections in here. You can see more clearly the sections here. There's the sort of carbon coming in as it's traveling over these rivets. And here we go. This is 400 microns across. And then you've got the zone on the outside, which again, it looks like it's another, I would say, 100 micron field around the outside, which is exactly as Savatomova was saying. So yeah, so this is a 400 there, and this is 800. So it's at 200 microns. It might be 200. Yeah, 200 micron field on the outside, and that on the inside channel. Okay, so it's actually over 100 microns. The sweep coming in. Okay. So how does that compare to what is in Matsumoto's work? In Matsumoto's work, the central area is maybe about 200 microns, and we've got about 100 microns on the outside here. So it's certainly of the same order of magnitude structure as the one observed in the clamshell of the supernova reactor. Okay, and I don't know what the material was that was in this Itonic cluster, in this micro ball lightning. One might argue, given the fact that this is a similar type of structure to it, with the segmentation, it might be a similar material. I don't know, but anyway, there we go. Right, let's get back to the main thread. So I was talking about this ball here, and its field of carbon around it, and its line going in, and you can see very clearly on the video the context of this ball with its wider environment. Right, I'm going to go and get another image, which is a very broad image. Actually, in the video that I shared earlier today, there was a moment which I zoomed in and zoomed out of something. I thought it was interesting, and I talked about this earlier, and I came out, and it was only when I was going home on the train I thought, really, that is absolutely incredibly interesting. I reviewed it on the video, and I wanted to sleep, but I couldn't. I thought this is just too much. It just couldn't be possible, but it was, and that's there. So then I started spending a bit of time, and I haven't looked at all of the SEMs, and I'm going to go to the Eastern Plateau and do a lot more searching there. But anyway, here we go. So do I want that one or that one? This one's 33. Of course it would be. Yeah. Okay, so we are in this one, and I want to pull layers. I want the layers down here. So first off, we're going to have a look around it, and this is actually 8K, so we can really go in. So what we can see is the balls often are buried into the surface, okay, but not always. And in fact, I don't know whether it was in the video that I shared earlier, but in some other recordings I have it where I'm firing the beam at the ball, and it literally jumps, and it just leaves the carbon circle with the nothing in the middle left. But you can see there's a smaller ball down here, which doesn't appear to have many crenellations on it. It might be a similar one over here. So these possibly would leave different interaction marks. This actually might be where a ball was. It's difficult to tell, but without looking at the SED, the one that gives the topological information. But we're going to have a look at some more balls before we come to the money shot. So essentially, this is what I'm talking about. So here you have a ball, and it's come over here, but look, there's something swept around the right side of this. And if we go over here, there's another thing swept around the right side of this, but the ball may be buried under here. It might have burrowed in over here. Don't know, or it may have been there and it came out of its own accord. But definitely there was a ball at the end of this chain. Now it might be that the coherent matter is, as I showed you on the crop circle wheat sheaf, or on the outside of the Lion reactor quartz. It might be that this is an instance of the material that was in this original which was in another structure over here. We don't know. No comments, please, on that. Anyway, so we got another one up here, and notice again, it's sweeping around the outside here, sweeping around the outside. So I believe there's a vorticity going around here. Okay, very, very, very intense. Okay. Again, up here, I believe there was a ball here, and you can see the sweep around, but this one wasn't bound. You can see that actually, if it's not buried, this is maybe in contact with some of the material as it instanced out of the coherent matter. But I think sometimes it's not bound sufficiently. So, and when you actually look at this, you start looking at this, it looks a bit like the Orion Nebula, where you've got stars forming on the end of these fronds of otherwise lighter, less dense material. It's literally like a nebula, and I'm pretty sure that all the same things will be going on, just on a very different scale. Okay, we've got another one down here. Over here, you can imagine there might have been one over here, but maybe not. And maybe it's buried. There's a couple of little ones here in their own little thing. Oh dear. So this is really rich pickings. This one's got its own bit on it. Yeah. Where else are we? Down here. Okay. Now I'm going to show you something which is a blow up. It's a blow up of the image which I just captured from the still frame. You already have seen it, but I captured it from a still frame, and what I will say is that the encoding on YouTube, the actual frame is 1920 by 1200, and it's scaled that to 1080. So there's a loss of quality plus the encoding loss of quality. But because we'll be able to zoom into the original image in this, you'll get the higher quality. But when you see it, I hope you're as delighted as I was when I saw it. You have to bear in mind that when I predicted the structure of these things, I did so before Henk had even started this experiment that produced the Vega Valley. And it was really based off just looking at John's sample that he sent me. So really, this is a team effort to get here, or across many, many decades. And thankfully, John actually held on to those samples, and for whatever reason, and I've talked about it in the past, that particular sample made its way to me, and the rest is history. So I'm going to, where is it? So I've got this one in higher detail here, and when you see these structures, they are generally all sort of around about 1 micron. These segments here. I'm just trying to find the particular image in question. I'm going to show you this one because it does show you in a number of instances where the carbon just comes out at the end of the thing. So I focused on this in the video, and I have a zoom in on this. But all over this sample, there are the balls, like here, and they are in their own little carbon fields. Okay, so for me, this is the technology that could probably explain abiotic production of hydrocarbons. I mean, I'm not so sure, for instance here, I'm not so sure that these structures are not these balls which have then had material laid on top of them. Okay, because this is copper, which is condensed, and underneath it's got zinc oxide. I think it is. No, maybe it's the other way around. But it has these deposits on top. So there may actually be many more balls than you currently understand there to be. But the important thing is, on the Vega Valley, north of here, or rather, shall I say, west of here, is the main channel. That is where the ball lightning coherent matter structures are forming. And why are they forming there? Well, firstly, you have brass. Brass in a residual air atmosphere produces copper oxides and zinc oxides. And in Something Electric Part 1, I discussed that the copper oxides are photoelectric, and I discussed that the zinc oxides are both thermoelectric and piezoelectric. And so you have an almost perfect environment for electron emission. The only thing that would potentially make that better is diamond. And this technology produces diamond or carbon. And carbon in the form of diamond is the world's, especially if it's slightly impure with nitrogen, is the world's best electron emitter. So we have electron emission potentially down the line. We have thermoelectric, photoelectric, and piezoelectric emission. Okay, that goes into a channel which forces electron bunching. The electron bunching forces coherence of electrons. Coherent electrons force the production of fluidized electrons, and that leads you down to the path of where Rodionov and Savatomova are, in which then you have ions, and the ions come into this Bose condensate superfluid superconducting material, which is a magnetic fluid, and it then produces these structures, and then they leak out, and they come down these channels, and then they start to get to the end of their life, and they start to deposit their payload. So at the end of this channel, there was something happened here, but if we go down here at the end of these channels in their carbon fields, we have one ball here, and a little bit further down we have another ball here. And so I think categorically we can state that it is that gap, and it's a very simple experiment. This can be replicated by any semi-competent teenager, I would imagine, with some safety surrounding the high voltages by another competent individual. But this is not something that needs high budgets, and it's not something that needs a particular number of letters after your name to replicate with absolute certainty. So here again, we have another one here. I've got these into different contrasts and stuff so you can see them. There's another little ball here in its carbon field. Some are out of focus. There's another one there. Oh, look at that. There's a lovely one at the end of this channel. Look at that. Look at that. Just nigh on perfect. And this is interesting because, as I said, Matsumoto used copper as his witness material. And this is effectively copper and zinc and oxygen oxide of that. So it makes it nice and bright. So the carbon shows up very, very clearly on these structures. So here we go. We've got another ball here, and this is the one that I showed you at the beginning. This is that's the title slide of this. So you can see that probably it came out of this channel here, and I'm not so sure that this entire area isn't one event or a couple of events, and you're seeing substructures. As I said, the ball lightning that was created by the explosion of Oretskev of titanium foil in water, and it came out and formed above the reaction chamber. It then, a few milliseconds later, produced small ball lightnings that went off themselves. Matsumoto saw the same thing. We have the physical evidence that exactly the same thing happened with a Masa gas on the 10 yen coin, because around the periphery you have substructures that are self-similar but smaller structures of the same thing, and then within one side of that you have little ball lightnings that moved around and took the oxygen off the copper and made sulfur. And so you have transmutation, and you have a substructure of a substructure of a substructure doing the work. And so I think it's pretty conclusive, to be honest. All that's left now is someone important to take the credit. Basically. Oh, there we go. There's another ball there. Now, this ball, I think there's either a buried ball here, or there was a ball, and for some reason it came off. But there's no doubt in my mind there's either a ball under that carbon, or there was a ball there. Anyway, they're all over. There's one here that obviously jumped and sat down in the middle of the field here. Still got carbon around it. It would do. Now, have I got any layers on this one? Is it this one? Oh, yes, I do. Okay, all right. You'll know what I'm going on about in a minute. Okay, so on one of these images, I mean, this one here is like a little meteor with its like contrail behind it. Look, oh, love it. It's just lovely. Everywhere. Look at this. Oh dear, love it. Okay, I'm gonna show you something which was the thing we zoomed into now, and it's a great pleasure and honor to be able to share this with you. Okay, so this was the thing I zoomed into. Boom! What do we have here? Well, firstly, we have our ion type structure of our coherent matter that's come out of its coherent state. And this looks like it's kind of like sliced through the top of the carbon field. But I'm calling this carbonite because it below here and around the side and into here, it's kind of underneath the carbon field. And so it didn't have a chance to form the crystals in the sort of iron crystal state. And I'm summarizing my hypothesis here. In these particular places, it didn't have down here, so you end up with smoother. But what do we have here? We have our segments, and we have our pinched segments, and with a curved bits on the outside. I believe that what you are looking at here is a segment of one of those balls, or just a not fully produced structure. This isn't a 48 ring structure. This is a 24 ring structure, hence the name of the thing, 24 segment toroid. And you're going to see a lot more, but this is the one that I saw. And as I said when I was making the structure, I'm only putting 48 there because there's 48 on the witness mark on the aluminum. And it might have been that in the case of that aluminum, it was formed somewhere else, or it was in the environment, it just went bang and hit the surface, did its work and bounced off. So there was nothing there, or it was just a field structure imprint that occurred. But if this is like a Guion, the area in between here would be intense electrical, and the gap in between would be your magnetic. But I'm arguing that these form basically like its own little collider in there, circular collider. So I'm saying that these are made of subsegments, and you can see maybe there's a segment there, and a segment there, and that these, on this case, broke off. So it doesn't form a full loop. but this got frozen in carbonite. And you can see that if I put the scale over the top, this is 2 microns. And so on the outside, you're looking at about 1.75 microns. And on the inside, you're looking at about maybe 1 micron. And the distance here and here is not quite the same. It's slightly pinched into the middle. But you have to remember that this isn't how it is when it's actually in its coherent matter state. This is how it is when they've regained the electrons and the wave function has collapsed and it's produced ordinary matter. Okay, so you're seeing the aftermath of the collapse of the wave function in the coherent matter. Okay, and this is a tori, I believe, of tori, or at the very least, a tori in this case of U's of these filamentary structure from the Rodionov and Savatomova work. But I believe you'll see that these actually are tori in other examples. And so there we go. For me, when I zoomed, and that's actually a still grabbed from the video. Okay, so that you've already seen this. I zoomed into it quick and went away. I'm going to look at this in a lot more detail. Okay, right. So what am I? So I actually spent a bit of time saying, oh, have we got any other examples in the images we've grabbed? And so I went through and had a look. And yes, we do. So I'm going to look on this one first. Okay. And they are here. And I'm saying that this might be a very large EVO here, which was like 100 micron across, that blew up. And what you're seeing is the little ball lightnings that come off from the explosion here. Okay. And what you're seeing is the guts, the carbon guts of the inside of the EVO. Okay. Of the cluster. I'm going to turn off the background here and you can see what we see here. Okay. And these are not all complete segments of things, but I'll go into this one in the middle here. And you can see it's not so clear, but this one hasn't got the outside removed. It is a D4D. Sorry, I didn't show that on the other one, did I? On this 24 segment tori, I've got the measurement here. So it's D4D structure, exactly as observed by Bostic and Nardi in 1970 or 1980 in their paper, and as observed on the structures on Hutchison effect. So what I am categorically saying tonight, categorically, in my view, the ball lightning is the key to both Lena and to the Hutchison effect, and to pretty much clusters are pretty much the cause of all exotic energy technologies. All, bar none, they're all this. So here's our torus in the middle here. Over here, let's have a look at this one. Less clear, but, you know, now I know they're there, I'm going to spend a bit of time looking at them in more detail. So we're going to expect these things in much higher fidelity. Thanks to your support, by the way. Look at this one. I love it. Look. 1, 2, 3, 4, 5, I don't know. But I would say that this has maybe 1, 2, 3, 4, 5, 6, 7, 14. Is it 14 around there? Is it 12? Maybe 12. 12, 24, 48, maybe. I don't know. Okay. So this clearly is toroid. It's a toroid of toroids. Okay. Toroid of toroids. This one is not so high fidelity. Okay. What have we got down here? This one, I think, is a blown up fragment. Okay. It's kind of a little bit left over of a probably a sphere. In fact, I think that all of these parts are part of a large sphere. And we know what the major structure is. Now look at this. This is absolutely beautiful. You actually see a breakup of the substructure here, and you can see the fragments here and the carbon around them. So each of these substructures are their own coherent matter structure, and they are still able to act in a similar way to the macro structure. Okay, and you can imagine that maybe you have, as Savatomova and Rodionov are suggesting, and as Matsumoto showed, in fact I can show again for those that are not aware of this part of Matsumoto's work, in his photos of electronuclear collapse, you have these hollow balls. This is with lead, so the lead will have a different structure, and actually in maybe later today I will show you what I would class as an Itonic cluster on a Mars palladium coated, which is interacting with copper carbonate, and it's really beautiful. It's really, really beautiful. Maybe I can show you that image in a little while. But you have these hollow balls. This is an exploded one, right? Okay. This is a carbon plume coming out of a lead ball. And where are we? These are other ones, different structures, Itonic clusters, different structures, Itonic clusters. There's a kind of flat folded collapsed one with eddy currents on it. There's more with carbon plumes coming. This has got carbon coming out of the center of the ball. Carbon coming out of the center of the ball. Okay, and it has this segmented structure, but it's not quite as clean as the one we had. It might be that the segmented structure has got, I don't know, corroded in some way, but this is lead, so it won't necessarily present itself when it comes back into our normal matter environment when the wave function collapses. But here's our segment. So I believe that this is a fragment of the overall structure, and I think we got some more. Where is it? I'm not so convinced on this one. Well, I'll need to have a closer look, but maybe this is another fragment of a structure. But I believe that the positioning of all these structures, there's another one up here. I quite like this one because it's like a smiley face. Look at this. So this has a couple of segments and then a bunch of segments joined together, and maybe a little bit in the middle. Okay, so that's that one. Okay, so you can see from the field. Oh, and I missed this one down here. This is beautiful because this really shows. And when I'm going to take a closer look at this, this is close to what we observed with Matsumoto. So you have 1, 2, 3, 4, 5, 6 segments radial, and the carbon around the outside. So I'm going to really look forward to going in and getting these in much higher fidelity for you to absolutely categorically prove that this is how it is. Whether people are upset about it or not. It is ball lightning, it is Itonic clusters, it is, oh dear, so much life. I don't want anyone to be wasting more life, really. It's done. I mean, let's start using it and deploying it and understanding it more. Okay. Right, so then we have, is it in this one? Yes, it's in this one. So in this one I have a couple more segments here. This one's buried. Again, this actually just looks like a ring of 2 spots joined together. It's buried in the carbonite. So I'm looking forward to having a different contrast and higher detail view of this. But you can see it's like 2, 2, 2, 2, 2. It's like it's 2 chains on top of each other. What else have we got? Oh yeah, this is beautiful. This is absolutely, this is more like Matsumoto's. Look. So you can imagine there was a ball here, a small one maybe, and it blew up, and you've got one little segment of it, or it's just a ring and it landed. You've got a couple of pieces here, you've got a few fragments, and then you've got one curved section, and then you've got the carbon left over. Let's go and look back at what Matsumoto had. Where is it? It's around it's early work, isn't it? Is it there? No. Let me find it. Let me find it. It's not that early. Oh yeah. I think that on this Vega Valley we'll find an exact equivalent of this, but I'm pretty much sure that what you're seeing here is not too dissimilar to what you're seeing here. Not too dissimilar, except in this one you see the witness mark of what happened, and in this one you see the witness mark plus you also see a bit of what actually caused it. Yeah. I said to a number of people this week that, excepting my family, I can be totally happy with what I've been gifted in my life, being able to share this with you guys tonight. Really, you couldn't want for more out of a life than to see this level of detail about how one of the most influential structures that works at every scale in our universe. To have this opportunity, it's just beyond imagining for my life. Here's another segment, and you can see this bit's blown out. It's left a carbon trail, and there's a couple of fragments over here. And again, these fragments will be the little kernels that you see on the outside of the more coherent matter that we actually showed right at the beginning here on this structure. So you've got the little kernels on the outside, and then this is the structure that's more coherent on the inside, and these are hollow balls. I can categorically say that when someone takes one of these balls and does an ion beam cut of them, it will be a little half sphere. I can categorically say that. I am totally certain that that will be the case. So there we go. So that's up there. This one here, this is the one of the money shots for me, in terms of categorically stating how this type of process works. And I'm looking forward, as I say, to capturing these in much higher fidelity in the next session. And that's it. It's done. It's done. Doesn't have to be ever done again. People can replicate it because it's easy enough to replicate. I'm just going to show you some of the elemental analysis because you get to see the proportion. But for me, this was the one that I kind of looked at, and it was like, that's it. That looks interesting at a distance. I zoomed in, going, oh, it's still interesting, and zoomed out, and then it was just on the train home. That I thought, oh my god, that literally cannot be. It cannot be an equivalent of. It can't be an equivalent of this. It can't be. It can't be that easy. It can't be that easy. That is that. I mean, this is 24 segments and a different number of segments there. But it's the same principle. It's the same principle. Well, actually, RTC Pet Science, however you say your name, they do like ferrofluid. Yes. Sorry, you lost signal. Did you lose signal? Did anyone lose anything? I don't know what you. Sorry, is it just you personally that lost signal, Corky, or is it other people? I don't. They're so. These are such key images. I don't want people to miss them if they're. I think I've got another. Oh yes, I've got another one on this one. Look at this. It's a little segment down here by this ball here. So the rest of the ball is there. But there's a little segment here. And I believe that when I look at these things in much more detail in the coming weeks, I haven't fully looked at this image, and there's other images as well. Yeah. For me, this with the D4D ratio and what was it? The one up here. This one's beautiful. I don't know how many segments this has got. Count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This might be a 24 ring too. but it doesn't have so many. I don't know. I'll have to look at it in different detail. But yeah, this is so clear, showing the process. It's just 100%. Matsumoto was taking pictures of electronuclear collapse or the aftermath of 100%. There's just no doubt. Well done, sir. Yeah, so I like this one because it's a bit squiffy. I like this one, and because it didn't fall apart and segments didn't come off it, you can actually get to see the structure here. Well, you've got to imagine, actually, it's not necessarily a part coming off it. In the coherent matter, it has the ability to spawn many of itself, because there might be more matter in there than is required to make individual spheres, if you know what I mean, if that's clear enough for you. It might not, one sphere might go blip, 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 and drop down a load of spheres. It's a little bit weird to think about, I have to say, but I think we'll find that's the case. Yeah. Okay, so let's go and have a quick look at the SEM images. And like I say, now you've seen this today, when I look at some data from one of the Hutchison samples, the knee sample, looking inside one of those triangles, and when I look at the microscopy images of the knife that sunk into a block of aluminium, which I had an opportunity to review with a microscope in July in Scotland last year, it will be clear that 100% that is this process. 100% categorically it is. Okay, so I'm going to load up a couple of the analysis. And then we're done for the night. Woo! If people want to hear, there's going to be a video question and answer tomorrow night on the American Anti-Gravity Society for about 2 hours. So people can ask me any questions live on that stream. Okay, Eastern Plateau balls, the device, the Phenom XL or Pharos XL device is made by Thermo Scientific. And what do we have? Right, so this is the first one you see, and I've just got a composite shot here. Now, why am I not seeing anything here? Well, that is because the electron beam is over here, and this is raised up quite a bit, and so it is shadowing, so it can't get any X-rays back from over here. But essentially, zinc boils at the lowest temperature of all these elements, with the exception of oxygen, obviously. And so you get zinc deposited from the copper after everything else has done what it's done. And that's interesting in its own right, because there's no zinc on the top of this, which kind of implies that this might have been active all the way to the end of the thing being shut off. When the zinc came down, this coherent matter blob, which was somewhere being excited by a nice ready flow of electrons, suddenly decided to collapse and come across here and spew out a load of carbon, as we observed in Matsumoto's work. Okay, so this is essentially pure carbon. If we look at it here, you don't see, well, actually, it's looking at the whole map rather than the spot in this case, but even looking at that whole map area, it's still got a high concentration of atoms of carbon in that whole area. But if we actually go and look at, I think maybe I did spot, oh, there's the carbon. So you can see that's a lot of carbon on the tail. The oxygen's everywhere. And the iron is definitely only here. Or maybe that little splodge down there. But yeah, it's definitely an iron ball. There's some random copper blobs. And there's the zinc everywhere. Okay. Often on these things where you get the iron, it's reflecting the basically an electron comes here and it bounces off and comes back, and you get an X-ray, and it's not on the actual ball. It's much purer than it would appear. Okay, so I take a spot sample on here on the carbon tail, and we see that is 85% carbon, and the residual copper and zinc are almost certainly where the electron goes through that carbon and gets a few X-rays coming from behind, or some reflected X-rays. I don't think this is absolutely, I don't think there's any copper or zinc there. There may be some sulfur. We know that ball lightning, when it blows up, leaves a sulfurous smell, and we saw sulfur synthesized by microball lightning on the 10-yen coin exposed to a Mars gas. So it's likely that is a real thing, although it's a small signal. And I think that the carbon, the oxygen may be just something on the surface, or it may be just a small amount, because carbon is triple alpha and oxygen is quad alpha. Okay, so there we have the tail, and then the head is by weight, it's concentration. By atomic concentration, it's 40% iron and 56% oxygen. I do not believe the zinc, the gold is an anomaly there because it was forced to be in. I think it's not real gold. There's no silver. Again, that was forced to be in. So these are not real numbers. The zinc is definitely not there. But there could be other light elements formed on the surface. So there may be some silicon. We've observed that on the ones observed by Alan Goldwater, and we've observed carbon. So I think when you look at this is practically the FeO2 ratio we observed in the ball, in the first and second ball that we observed in the center of the Vega Valley. But note, these are much smaller. So this ball is about 10 microns. This is about 20 microns across. Okay. And then image 3 is the map. Now, again, in this image, if I can get the zooming right. Ah, dear. Don't like the way that does that. Let me try and do it this way. Okay. So in this image, maybe I can zoom here and it won't do anything. Okay. All right. We'll do that. In this image, we have our iron balls. There's zinc deposited on the outside. There's zinc on here and copper little splodges up here. But these are iron balls, essentially, with a little bit of oxygen. You can see a little sprinkling of oxygen there. Maybe I can zoom in a little bit more. Just get right in there. Okay. This is in shadow. This whole area here, this ball is causing a shadow there. You can see it very clearly. And there's a shadow all over here. So it means we can't see what this thing is that's sweeping around clockwise. All of them were sweeping around clockwise, okay? And we can see, though, that as it comes in, that it is essentially pure carbon, okay? So I think this material sweeping around here is very, very, high carbon content. And let's just zoom out. So in this whole map, wherever it is, oh no, why does it do that? Got to find out why it does that. Okay. In this whole map, this whole area here, nearly 67% is carbon, which can be observed. 20% oxygen and very little iron, yet the iron is on here. So this might be the fact that the beam can't get even only onto the top of the iron, but we know the balls are basically iron and oxygen. Okay, so there you can see is oxygen, and you can see the shadowing going on here. You see all the carbon. It's like beautiful. It's just beautiful. And then there's our iron balls. They really are iron and oxygen balls. And there's the copper. And there's the zinc. All right, so I have one more SEM set to show you. I don't know what I've got in here. What have I got in here? Oh, this was another trail somewhere else. The ball isn't there. Maybe the ball was here. I don't know. Maybe. I don't know. But in this central section of that, we have most of the atoms are carbon and oxygen. Again, we've got some residual sulfur, a little bit of chlorine, and the copper and zinc is probably reflected or captured. A different spot, a different color there, and we have a range of elements. So silicon, potassium, chlorine, aluminium in low ratios, and sodium here. So you can understand how this structure is able to synthesize the elements very important for life. Carbon, oxygen, sodium, not so much aluminium, chlorine, potassium. And another spot on this trail, and again, same sort of story, 10% sodium in this case. We are saltwater creatures. Sodium chloride, okay? And carbon, oxygen, and so forth, potassium. And I've got a line map here, and that's probably looking along the line. And you can see the various elements there. Carbon goes up on it. Oxygen's on it. As you get closer to this end, you get more and more sodium. The tail end, at the back end here, you get more aluminium. The back end, you've got more silicon. Pretty consistent throughout on chlorine. Potassium. Copper is just coming off the end of the line there. There's a bit of deposited zinc in the middle. Anyway, that's that. Okay, so what have we done today? Well, I would suggest that we have shown with reasonable certainty how ball lightning forms. We've replicated many of the observations, but not necessarily the interpretations of Takaaki Matsumoto. But these structures can form segmented rings. They can form spheres, and they have fairly predictable, in fact completely predictable, fields of depositing carbon and other light elements like silicon and so on. And it could be very likely that the iron is synthesized in them, but it doesn't necessarily have to be. It doesn't necessarily have to be. And that might be why, Yul Brown added iron to his radiation remediation. It's just a good anchor for all the action to occur. But certainly I would suggest that they are hollow balls, and I think we have proved that they are hollow balls by comparing the work of this analysis by Alan Goldwater in his Magic Sound lab in an ultra experiment to the work of Takaaki Matsumoto in his experiments, and showing that the structures that are synthesized here have these very coherent glassy-like structure on the inside and these kernels on the outside, and this is as it interacts with a material. And so I think that's pretty much what's going on there. And we showed that the ball lightning produces traces like the coherent matter traveling waves that we've observed and recorded on video in VEGA experiments. Thank you, Henk, and thank you, Dave. And that at the end of the day, it produces an identical format of structure from where a ball lightning hit the ground. And actually, I believe that any super energetic process, like a meteorite coming in, will produce these things, an airburst of some cosmic interaction coming in. But I believe that at the head, Ken Shoulders said that every feeler, so as a lightning comes down, I think it comes down and it gets over energized, and as you're seeing on the eastern plateau, it splits, and each of those splits of your feelers for your lightning, according to Ken Shoulders, will have an EVO in, or a ball lightning, and that does the ionization of the channel. I believe that every single one of those will have at its core a something like you are seeing here, and that those people that go around in Norway and collect so-called micrometeorites, they're most likely, in my view, collecting the cores of maybe lightning. But of course, they could be micrometeorites, because that is a very energetic process. So there is some crossover between the two. Okay. And we saw them on various structures. And so there we go. And we talked about geons. And we showed that these are clearly sweeping around in a very particular direction, and so on. And so that might be to do with the way the electric field is sweeping around in a very particular direction, and that the clusters are clusters of clusters, and again that is borne out by the work of Takaaki Matsumoto, and I think it's in this image, and if I zoom out a bit here, these are these clusters, and I don't know whether they're making or breaking at this time, but you can see how they wet into each noodles, into each other to form like noodles that then you could imagine would go and form a ball, and that this kind of wetting process is what creates the Vega Valley itself, but also what we see in the ball lightning forming on the anodes in the Vega experiment. And so that's that. This one's got a problem loading the page. I don't know what that was. Oh yeah, so we said that it generally synthesizes. This is a very, very key finding here, that helium 4 has no spin, and that might explain, based on the Rodionov and Savatomova work, why that gets synthesized, and other elements like carbon 12 and oxygen 16 and calcium 40 and silicon 28 and silicon 30, why these are preferentially synthesized. And then in the Rodionov and Savatomova paper, they proposed, based on work by Matsumoto and other and some Russian authors, how these filamentary fluxes produced are surrounded by coherent electrons, effectively fluidized electrons, superconducting, capture ions, and it's in this field around these structures that you get the synthesis of elements. And I think we've categorically and 100% shown that that is the case, and it favors carbon, and why would it not? And so there we go, and we have these lovely demonstrations of these particular structures around this particular thing. So here, a nice squidgy one, not so clear on that one. All these ones I will have a look at more detail. A fragment of one, this beautiful fragment with sections coming off, this group of fragments, this group of fragments here, this cluster here, kind of like a knotted segment of cluster. And in this one we have some more sections. This beautiful, beautiful, absolute wonderful analog of Matsumoto's work, and this one. And then the money shot that revealed it to me, this 24 segment structure here, which is a D4D ratio. So with that, I suggest that we are getting to the end of understanding what is going on with ball lightning, and it is real. It can do Lena. So I'm gonna just see if you've got any questions there, and then I'm gonna call it a night because I'm exhausted. So Daniel Foster, it's called GEON, and you can go and look at the link to the paper on remoteview.icu on the latest blog post. Yes, thanks to my darling wife and to all the people that have supported this work, really. So, hey Bob, I just got 1,000 times magnifying camera. Is enough magnification to see the tracks on aluminum? You should be able to see tracks at about 220 times, which we did using the Narugo and using, which is 400. Narugo is about 400 times. 200 times, 220 times is what we've got on the Dynalite Edge, and we witnessed that on ultrasonic produced tracks. So around the EVO, we would expect a swept skirt on the surface, which is what we observed. Absolutely. I suppose the equatorial disc and EVOs absorbing 50% into the surface are related. Probably. I have a ½ pound of ionic gold rock. Good for you. The repeating pattern at different scales seems to be ball with vortical accretion disc and jets emanating from the pulse. Yeah, actually, there's one thing I want to talk about. Actually, that's reminded me. Look at Savatomova's and Rodinov's image here. Now, whilst you've seen more detail, if this is akin to the spheres, you can see that you have a straight line through and it comes out at an angle, and this might explain the kind of marks that you see, and you will see, by the way, because I analysed the steel vibrator plates of Roish Amasa that I acquired in 2019. And you will see a very, very spherical cutout with two little triangular nicks. And it kind of points to what's going on in the ultra experiments as well. So maybe we're expecting the magnetic clusters to form at those points, and we've got more evidence to share with you that points in that direction. But certainly it would appear that the clusters form in the ultrasonic systems as well. Okay. So someone's saying that's a 16 ring. I can say that we've got one with good clarity because I spotted something interesting and looked into it and came back, and then I just had to find the other ones. Unfortunately, the 8K images were good enough to be able to find them with reasonable certainty that that's what they are. But I'm so excited to be able to get back onto the SEM and get really high resolution images, because that particular structure here, it's what is it? It's 2, 4, 6, 8 microns across. I think we can get a better image of that, or rather, we can get a better image. This is actually zoomed in, by the way, so this is 9,700. But we can go into like about 20,000. It does get a bit fuzzy at 20,000. Certainly at 10,000, it's relatively clear. But we can get similar quality images for all of the other ones that we were looking at, like this. This is, if we look at the scale on here, if I zoom back out on that, this is only at 520 times. Yeah. So if I go back to that, that's only 520 times. So we know from where is it? Not that one. We know from this one, we can go to, what's that? 5 to 20 times. We can get get 20 times the fidelity on this. So this is just going to be absolutely crystal clear. There's going to be no shadow of a doubt that what's going on in these systems is what's going on. It's going to be, there's no debate. It just is going to be what it is. I can't wait. What magnification have I got this at? This is at 710 times. So again, we're gonna be able to go like 8 times more fidelity on this. It's just gonna be really absolutely categorical. So I must thank Stephen and Charles and Sho for helping support a lot of the SEMs that we've done recently and over the years, because whilst you say you can't imagine, I did kind of imagine by taking a microscope against the Hutchison sample. I could never have imagined that I would actually have the opportunity to see the reality of these things. It's just a thing of incredible certainty. It's just wonderful, just wonderful. It's kind of literally exactly how I imagined it. It's just coming up with that EVO structure. It was a lot of sleepless nights because it kind of had to be that wherever it is. Where is it? Oh dear. It had to be. I had no choice but to accept that is what's going to be. But would I ever see it in my life? Would I ever see the actual thing that caused it, rather than the shadow of what its aftermath? And there it is. It's just there. Yeah? Oh dear. So lucky. So lucky. Okay, I'm going to have a look at your comments down the bottom. Okay. Sumner Stewart, do protrins create EVOs? I think you mean protons, maybe? They are very important. Firstly, they have a magnetic spin, so they can be captured in by the electron condensate. But when they're in there, they will go and build other atoms. Thank you, RTC. How is fixing Fukushima coming along? Slobodan Stankovic is rebuilding the HHO generator that he built with his father, and so that's coming along nicely. We now have fully characterized that the samples are radioactive, that they have thorium, and we now even, from the last videos that I shared this week, we know which grains contain the thorium. The color of the grain is like an amber color, and it's clear. Surprisingly, I for whatever reason I thought it was the more black shiny ones, but in fact they are iron and so forth. So they contain things like neodymium, and it's just wonderful. But yeah, so we know, and having seen what I've seen here and the importance of iron to the transmutation process in exotic vacuum objects, it might just be easier to feed a little bit of iron into the process, as was done by Yield Brown. Of course, the sand as it comes has iron content in there, but not in the grains. So I don't know. I don't think it will need it, so we can do it with and without. But we've come up with a concept where we will put it in a tube, and because we'll be focusing on the gamma emissions, it doesn't matter if it vitrifies or whatever. We're not worried about the beta or the alpha. We're only going to be looking at the gamma. But we will put the processed crucible in the middle of his reaction. His spectrometer, his emission spectrometer, and we'll have the other devices there, and we'll try and automate the process so we're not in the room, because there could be a large flash of radiation, but I don't know whether that will occur. It did in other cases of strange radiation. I don't want to be there for the strange radiation pulse, and really the whole area needs to be properly shielded, but I think that when it's in the coherent matter and the matter collapses, I think it's only strange radiation we need to worry about rather than a gamma flash. Anyway, we will be able to observe, hopefully, the change in gamma afterwards, emissions from that amount. The question is, 35 cc's is producing a quadrupling or tripling of a large signal of gamma. How much do we need? Do we need 1 cc? Do we need 5 cc's? You know, but even then we have like whatever it is, 35 cc. So we can do 7 experiments, I guess, at 5 cc's. So we just need enough material to produce enough gamma to be able to detect the before and after if there's any changes. So. Ken Pratt, I don't have an understanding of that, but yeah, so I can't really talk to them about that, Ken. Stephen, yes, I will talk about that. In fact, I met the author in 2019. The secondary cone, the pulse frequencies. Yeah, no, in fact, I'm going to talk about Tesla's radiant energy because it is exotic vacuum objects, it is charged clusters. I will talk about that in the translation of Alexander Shishkin's work, his most recent work, which I was going to do, but then I got an opportunity to use this SEM, and so the last 2 weeks has been about using that opportunity to do work that has been stalled for now 2 years because of silly nonsense, draconian and fascist rules, so you have to take the opportunity when it's there. But yeah, we need to consider that might be the case. To a certain extent, we're exposed to this kind of radiation from all kinds of different things, and the Russians say don't work near spinning bodies or do welding, but lots of people do. Okay, so I thank you very much for your participation in this evening's reporting and discussion. It is an honour, it's a pleasure to be able to share this with me. I just feel like the most luckiest guy on planet Earth right now, not only because I have a wonderful family and all of that, but also because I've had this opportunity within my lifetime to be able to see physically how one of the man's most spoken about and debated mysteries occurs, and how it relates to other mysteries. And I think the most important thing for me about what I'm seeing here now is it's a realization that I had in 2017, but all the pieces were there, from the archaeological record, from the experimental record, from the anecdotes, and from the architecture, that something was known, and it's very, very clearly the same thing across many cultures and many technologies that never quite made it. Something was going on that was consistent. And what was that? And this common factor is like, when someone's telling you it's ball lightning because they have it in the name of their conference, maybe it's ball lightning. When Ken Shoulders is telling you it's ball lightning, it's probably ball lightning. When the US military is telling you it's ball lightning, it's probably ball lightning. I mean, when Matsumoto is saying it's ball lightning, it's probably ball lightning. So maybe it's ball lightning. But then what is ball lightning? And that's a mystery. And what are all these things that are happening around it? But to have this opportunity, I just couldn't have wanted anything more fulfilling, really, in my few years. You know, it's only been made possible by people that have had the guts to support the work and I actually, you know, I didn't know about Wheeler's work until after I shared that structure, but learning about Wheeler helped me understand other things and to realize that, you know, as ever, the same thinking is going on from different angles. And why is that? It's because we're all saying the same thing and we're all trying to interpret what we're seeing. Well, now we're getting to the point of physically seeing exactly what it is that is doing this work. You know, it's just amazing. All right, so I'm going to say goodnight. I'm too tired and I need to sleep because I've got to be up tomorrow late as well, and I want to do these 2 Hutchison samples on Sunday. So it's going to be... I had to get this out before I did the anti-gravity meet yesterday because it was too... it just had to be out the door. I can refer to it and people can then go and have a look at it. So thank you very, very much for your time and your support. And buenas noches, buenas sera, dobro noc. Good night. Ciao for now.